this was the inverse square law business. Remember, it's inverse square because this distance is in the denominator, so that means it's inversely proportional to the force over here. And you can just think about it like the force will increase if the distance gets smaller. If they're closer together, there will be more attractive force or repellent force between them. If it were just F equals blah 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 over distance, then you get twice as close and the force would be twice as much. But because of the squared, if you get twice as close, the force is 4 times as much. Or if you get 3 times as close, it's 9 times as much because of that squared. But so it gave you a thing. It didn't even give you the charges, because all you need to know about the formula, you don't need to calculate the formula, you just need to know that it's got that squared in the bottom. And whenever a formula has that squared in the bottom, whatever's on the bottom, if it gets cut in half, this on the left will get multiplied by 4 because of that square. So it tells you the force was 50 when they're 6 meters apart, and if you move them 3 meters apart, so that force got cut in half, the force would then be 200 because that 50 would get multiplied by 4. So you don't even need to do the whole math of the formula. You just got to say, okay, it got cut in half. I know that it's the inverse square, so 50 times 4 is 200. Done. It makes it a little easy like that. And we'll practice this a couple more times. There's a question that's like this on the CTBA. And there's also a question that's not like this. It also uses Coulomb's law, so you're going to have to be careful. And what is going on over here? I thought I picked this up. This one. Yeah. Oh. So today's thing, we're going to use all of these rules, and we're going to use the formula V equals IR. There we go. V equals IR there. And I don't want you to get mixed up with the series. So here's a series circuit, and here's a parallel circuit. The parallel one is the one that's broken up into different little loops. And the series one is just one loop. So the only rule that we used yesterday was this total resistance rule. So for series, you just added them up. So like some of these will be easy today. You've got 200 ohm resistors connected in series. There's 2 of them. You just add them up. So 100 plus 100 is 200. But now it's going to have you use the voltage rule. So for series, you just add up the voltages. That's nice. And for series, current's the same anywhere in a series circuit, and that'll come in handy here in a minute. In a parallel circuit, we did this yesterday with all the weird inverses and adding up the resistance, the total resistance. And don't forget, if you're doing this in the calculator, you need all those parentheses to make it work right. And for parallel, so current's the same anywhere in series, but in parallel, current is split up between all the different components. So in a parallel circuit, if you got 5 little light bulbs and the total current is 5, then each light bulb gets 1 amp of current. And so current's the same anywhere in a series circuit, but voltage is the same anywhere in a parallel circuit. And we'll see more about how this works tomorrow. But today is going to be pretty much all right. Some of these diagrams it draws for you, but it will ask you to draw these other diagrams. So it says the batteries are 1.5 volts here. Don't forget in your diagrams, you got to put those numbers on there. If it tells you how much each thing is, you got to write that on there. It says the light bulbs each have a resistance of 1.1 ohms. You got to label all these light bulbs. And it's asking what's the current through each lamp. On your assignment, it asks you for the total resistance and the total voltage, because you have to find those in order to find the current through each lamp. So let's go ahead and do that. This is a series one, so for resistance and voltage, you just add them up. So we got 5 of these 1.1s. Those are the resistances, or those are in ohms. So the total resistance is 5.5 ohms, because we just added them up. 1.1 plus 1.1 plus 1.1 plus 1.1. Voltage, you also just add them up because we're in series. It'd be different in parallel. You got to go and look for which one you're in. Okay, it's series. You got to use the series rules. So a total voltage is 1.5 plus 1.5 is 3 volts. Once you get your totals, then you can go find your other totals. So we're not finding the total current. We're finding the total current. We're not finding the ones through each lamp. We're not finding the particular ones here yet. We're just going to figure out, okay, we know the total resistance is 5.5, we know the total voltage is 3. We're going to find total resistance. Total current, sorry. Yeah. So let's see. I'm going to use a different color marker here. 3 volts is my total voltage. I'm looking for current, and the total resistance is 5.5 ohms. There we go. I wanted to say equals I, so I'm going to divide both sides by the 5.5. 3 divided by 5.5. Wish I could remember what that is, but I can't. What do you say? Oh, that's right, 0.54, thank you. So I got 0.54 amps, and it's 0.54 repeating, whatever. No, oh, that's not the current across each bulb, that's not what it asked for. That's the total current. Total current there. So now we've got to go look at the rules. We're in series, so for series, current is the same anywhere in a series circuit. Okay, so that's the total current. Because it's the same anywhere, we don't have to split it up. If they were in parallel, we'd have to say, okay, 0.54 divided by 5 is, because there's 5 little light bulbs, right? So we'd have to split it up between each of them. If they were in parallel, we'd have to say, okay, they're going to be about 0.1 each, or something like that. But we're not in parallel, so for series, current is the same anywhere. The total current is 0.54. That means the current is 0.54 anywhere. And I know it's not a real total. We didn't add anything up to get 0.54. But if the total is 0.54 and the rules say current's the same anywhere, then it's 0.54 anywhere. So that will end up being the answer, but only like we found the total current, then we looked at the rules, and then we figured out, okay, that's also the total current across each lamp. But it didn't necessarily have to be, just because that's what the rules said. Seem all right? Well, please go try out that series and parallel. There.